All right, welcome back. In example 2.4.5, we'll be doing an example of the transition matrix outside of Rn. So I'm going to look at the following subspace of W. Consider W, which is a set of all polynomials in P2, so polynomials of degree 2 or less, which evaluate to 0 when you plug in 2. All right, I've already found 3 different bases for you. So consider the following bases for W. I have B, I have C, and I have D. All right, I'm asked to find the transition matrix from B to C. So P, B to C. I need to find how to write x squared minus 4 in terms of C. That's going to give me my first column. Then I have to find x minus 2 in terms of C, and that's going to give me my second column. All right, so let's do it on the side. I have to write x squared minus 4 as a1 times x squared minus 2x plus, actually, might need a bit more space just in case, plus a2 times x squared plus x minus 6. And so if I put it all together, I have a1 plus a2 x squared. I have minus 2a1 plus a2x, and I have minus 6a2. So I need a1 plus a2 to be 1. I need minus 2a1 plus a2 to be 0, and I need minus 6a2 to be minus 4. All right, so from the last one, you get that a2 is 2/3, and then you plug it into either the first or the second. In both cases, you'll get that a1 is 1/3. All right, so 1/3 plus 2/3 is 1. That's perfect. And so that gives you the first column. And then we do the same thing, but with x minus 2. So I want to write x minus 2 as a linear combination of x squared minus 2x and x squared plus x minus 6. Again, a1 plus a2 is going to be the same thing. I was being a bit thick. I'm using the same basis elements, so this will be exactly the same. And so that left-hand side, again, will be the same, just like it was for Rn. So you could actually kind of use a similar trick. You just have to show me this extra step to get the coordinates. But once you have this, you could apply it to both polynomials right here. All right, but in this case, it's so simple to find a1 and a2 that you don't actually need a matrix. So you don't need the shortcut of solving both systems at once. From this one, I get a2. a2 will be 1/3. And then I could use either, but from that one, I get that a1 is minus 1/3. All right, so minus 1/3, 1/3. All right, this is the transition matrix from B to C. All right, we're asked to find the transition matrix from C to D. Sorry, my D doesn't look like anything. Yeah, that's my cursive D. All right, so now I want to take the elements of C, the two basis elements from C, and write them in terms of D. So I need to write x squared minus 2x in terms of D, and I need to write x squared plus x minus 6 in terms of D. All right, these are bigger, so I'm not going to have the room to do it on the side. I'll do it underneath. So x squared minus 2x, I need to write as something times x squared minus 2x. Oh, that's not going to be hard. And then something times x squared minus 4. Right, let's not even do it. I mean, clearly this will work. And so my first one is 1, 0, right? This is exactly the same polynomial. Second, x squared plus x minus 6. I need a1 times x squared minus 2x plus a2 times x squared minus 4. And so here I would need um, minus 4a2. And so if I look at this, I need a1 plus a2 to be 1. I need minus 2a1 to be 1. And I need, so that gives me that a1 is minus a half. Let me move it up a bit. I mean, I could do it on the side, but I think it's going to be clearer for you guys if I keep going here. And then minus 4a2 should be the constant term. So this should be equal to this. So that should be minus 6, which means that a2 should be 3/2. So I get minus a half, 3/2. All right. Now I want to check that this composition gives the transition matrix for P to D. All right, so let's compute the composition. Let's compute the product of the matrices. I'm sorry, I'm so bad. There you go. All right, so PCD we just found was 1, 0, minus 1/2, 3/2. And PBC, we got an A. I have it in front of me, so I won't have to look up. So 1/3, 2/3, and then minus 1/3, 1/3. Now I'm going to multiply them as we do usually. I'll get 1/3 minus 1/3. I'm getting 0. And then I'll have, this is just 1. And then for this one, I'll get minus 1/3 minus 1/6. So that's minus a half. And then I get 0 and then 1/2. All right, so I have my candidate for the transition matrix from B to C to check. I just need to check if wait, let's see, what were the vectors? X squared minus 4. Is it equal to 0 times the first element of D plus 1 times the second element of D? Well, yeah, that works. And so this is indeed the coordinate vector of x squared minus 4. Let's check the next one. The second vector of B was x minus 2. Is x minus 2 equal to minus 1/2 x squared minus 2x plus 1/2 x squared minus 4? Let's compute this and check if it works. And so I get minus 1/2 plus 1/2 x squared. I get plus 1x, and I get minus 2. So in total, I get x minus 2. Perfect. And so yes, the transition matrix from B to D is indeed the matrix I just found. All right, so let's write this in the takeaway here. If I want the transition matrix from B to D, I can stop along the way at C and then go from C to D. So I'm going to start by going, from B to C, and then I'm going to be going from C to D. Right? Turns out that I'm not going to prove these takeaway 1 and takeaway 2, because they're direct consequence of theorem 2.4.2. We just need to apply it to the identity. So once you see that these transition matrices, oh, we did a lot of work. Once you see that these, wait, did I go too far? Yeah, I did. All right, that's what I thought. Man. All right, yes, good. All right, once we see that these transition matrices are just the matrix corresponding to the identity, every result that we had in the preceding section about representation of linear transformation using matrices apply to the transition matrix. And in particular, we get things like if you go the other way, it's the inverse of the matrix. So if instead of going from B to C, you go from C to B, it's just the inverse. And then if you stop along the way, then you could take a composition. And so that's one. All right, that is it. We finished chapter 2 and survived.